Sometimes we're going to have a function that is rational and has a radical in the numerator. So it's going to have two things going on. Well, for these functions, what you need to do is you still need to set the expression under the radical greater than or equal to 0 and solve for x. But then you also need to set the denominator equal to 0 and solve for x. So the domain is going to be the intersection of those things. So it's going to be all the numbers from step 1 except where the denominator equals 0, which is the number from step 2. All right, let's look at a couple examples of this. So this has an even root function in the numerator, and it also has a denominator. So what we need to do is first start by setting the expression under the radical, which happens to be x plus 1 greater than or equal to 0, and solving for x. This is a linear inequality. Remember, those are the easier ones to solve. Just isolate the variable, so I end up with x is greater than or equal to -1. Well, let's put that on a number line for right now. If I need the numbers that are greater than or equal to -1, here's my closed circle at -1, and then I'm all numbers to the right of that. But then it says, all right, well, you're not done because you have a denominator. You have to set the denominator equal to 0 and solve for x. Well, let's set that denominator of x squared minus 4x minus 12 equal to 0 and solve for x. This factors as x minus 6 times x plus 2. So I solve here, I get x is equal to 6 and x is equal to -2. So I need open circles at these numbers, at 6 and at -2. Well, here's -2, open circle, and here's where 6 would be, open circle. I have to now figure out how to write the interval notation of this red and purple number line that I've drawn up here. Let's read step 3 again. It says the domain is going to be all the numbers we found in step 1 except for where the denominator equals 0. So I need to write the domain of this function. I'm not allowed to include -2 in my domain because it makes the denominator equal 0. But was -2 allowed when I looked at what the numerator allows? No, -2 was never going to be allowed because my numerator said I had to be the numbers that are greater than or equal to -1. So I don't really have to worry about this open circle because it's not part of the red line. Well, if I want to do the interval notation of this shaded red line, well, we know that that would be a bracket at -1, comma, because I have an open circle at 6, I'd have to stop at 6, put a parentheses, then union, start back up at 6, and go all the way to infinity. So the domain of that function is from -1 to 6, and then because of a 6 has an open circle, we stop there parentheses, and union, start back up at 6 with the parentheses, all the way to positive infinity. Let's look at example 6. Same thing, it's got a radical in the numerator, and it's a rational function. So start off by setting the expression under the radical, which happens to be 9x plus 27, greater than or equal to 0, and solving for x. This is a linear inequality, which makes it easier to solve. Just isolate the variable. So I subtract 27 from both sides, and I get that -9x is equal to -27. Dividing by a -9, well, remember, when we're dealing with inequalities and we divide by a negative, we have to flip our inequality symbol. So this becomes a less than or equal to a +3. So let's put those numbers on the number line. So here's 3 on my number line, closed circle because of it's or equal to, and the numbers that are less than 3 are going to be off to the left. Now let's deal with the denominator. My denominator is x minus 1, so I set my x minus 1 equal to 0 and I solve for x. Well, I get that x is equal to +1. I cannot be this number. I must exclude it. So here is +1 on the number line. I need to draw an open circle there. So let's make an interval notation of this graph. Well, the domain of this function, if I start off to the left, the very left is shaded, which makes it -infinity. I'm going all the way to 1. I have to stop there with a parentheses, union, pick back up at 1 with a parentheses, all the way to 3 with a bracket. So the domain of this function is -infinity to 1, union 1 to 3. Let's look at example 7. Example 7 says, find the domain of this function. I have, just like last time, a radical in the numerator, and I have a denominator. So begin by setting the expression under the radical greater than or equal to 0 and solving for x. Well, this is a polynomial inequality. Remember, we solve these differently than we do linears. What we need to do is first determine the degree. Well, the degree is 2, which makes it even. Then the leading coefficient. Well, the leading coefficient would be 1, which makes it positive. So what is your end behavior? Well, your end behavior is going to be up and up. Then I need to find my x-intercepts. So set x squared minus 5x plus 6 equal to 0. If I factor this, I get x minus 3 times x minus 2 equals 0. Solving, x is equal to 3, and then x is equal to 2. Well, what is the multiplicity of both of those zeros? The multiplicity of both of those zeros is equal to 1. So let's graph that. Here on my number line, I'm going to graph this. See, we have 2 and 3. From 2, I go up. From 3, I go up. The multiplicity of 2 is 1, so I cross. And then I get to 3. The multiplicity of 3 is 1, so I cross. So take a look at the statement. The statement is greater than or equal to. So that means where are you above or on the x-axis? Well, I'm above or on the x-axis. All the numbers over here to the left of 2 and all the numbers over here to the right of 3. Right? But I'm not done. I now need to find out what I need to exclude from that denominator. So let's set that denominator, which happens to be x squared plus 4 equal to 0, and solve for x. If I subtract 4 from both sides, I get x squared is equal to negative 4. Taking the square root gives me x is equal to plus or minus 2i. Where can I put I, or an imaginary number, on the Cartesian coordinate system? I can't. Let's go all the way back up to the top. Remember, I said that you needed to exclude the real numbers that we obtained. Well, this is not a real number, it's imaginary, and because it's imaginary, I don't need to exclude it. So the domain of my function is actually just going to be what I've graphed up here. So let's write the domain of this function to be, well, this is from negative infinity to 2 with a bracket because of the or equal to bar, union, pick back up at 3, all the way to positive infinity. Let's look at examples 8 and 9. These are the ones that for some reason students get most confused about. So it says, let's find the domains of the following function. The first one is f of x is equal to 2x plus 5. All right, let's go back up to the directions for the beginning. I said when you're finding the domain of a function, you begin by assuming that the domain is all real numbers. Then you have to figure out, do you have issues? Are you rational or are you even root? Those are the only times that you have to do any work. Well, let's take a look at example 8. Again, it's f of x is equal to 2x plus 5. Does this function have issues? Is it a rational function? No, there's no fraction there. Is it an even root function? No, there's no radical there. So because it's just a linear, its domain is going to be all real numbers. Let's look at example 9. Same thing. F of x is equal to x cubed plus 2x minus 7. Always begin by assuming that your answer is going to be all real numbers. Well, does this have issues? The only time you have issues is if you are rational. Well, is this a fraction? No. Or if you're even root. Well, does this have a radical? No. So then my domain for this function is going to be from negative infinity to positive infinity. That's it for this section on domains of functions.